We finished up chapter 1, and so naturally we move on to chapter 2. Now we will be skipping the first section of chapter 2, and we will go on to the second section, and it's going to be all about circles. Circles, circles, circles. So let's define it real quick. A circle with radius r and center h comma k. So that is a coordinate. It's an ordered pair on the xy coordinate plane. Going to have a special equation, and the equation is going to look a little something like this. where x and y are variables, which means they'll stay written x and y in the equation. H, K, and R are going to be numbers in most cases. They're going to be actual numbers that are filled into the xy coordinate plane. So what we're saying is this is how we can read off the center of the circle. It's got to be a point. And then we can find, excuse me, we can find the radius of the circle. It'll be on the other side, and it's going to be squared already for you, basically. So this is, I would commit this form to memory, though we will be dealing with it, of course, here today. So let's try this out. Let's see what we can do with this. So how about we describe and graph the circle with this equation. X minus 1 quantity squared plus y plus 6 quantity squared, all of that is equal to 9. So remember all the way back to the basic definition of a circle that we just wrote, and it has it already being subtracted. So if it was x minus 1 squared, that means that the x coordinate of the center is really just the number 1. It's really just the number 1. In other words, what you see inside there, it says x minus 1 squared. You need to just take the opposite sign. So it says negative 1. So really the center is going to be the coordinate. 1 is going to be the x coordinate. And I just realized I screwed up everything there. So that's okay. And then the rest of it was this. So now we can get the y coordinate of the center. Remember, we take the opposite sign just because of the odd way in which the equation is meant to be written. So the y coordinate of the center is not 6, it's actually negative 6. So it has a center of 1 comma negative 6. It's going to have a radius. Remember, the radius is the distance from the center of the circle to any point on the actual the boundary of the circle. The radius, remember, the radius was written as r squared, meaning it's already been squared. In other words, you got to take the square root of what you see over here on the right-hand side of the equation. So it's going to have a radius of 3. What is it? So it's going to have a radius of 3 and a center of 1 comma negative 6. Let's keep that in mind, and let's try graphing it. So we can go ahead and we can get rid of the equation here. All this business up. I don't know why this doesn't want to get selected. Let's try graphing this bad boy on a standard XY coordinate plane. Now graphing, for me, we do obviously have to talk about some graphs here and there. But we're not, I don't get uber detailed with graphs. So let's see, 1 comma negative 6 is the center. So let's try graphing the center first. Let's see, we'll go 1 on the x-axis. And then do we need to go up or down 6 units? What are you guys thinking?
Down.
Down is correct. We need to go down 1, 2, 3, 4, 5, 6 units. And how about right there? Right there is pretty comfortable for us. Now we need to draw a circle that has a radius of 3. So in each direction from the circle, we can go 1, 2, 3 units, give or take. And now let's see if we can use the circle tool here. It's going to be weird. Let's see if we can draw an adequate circle. And I make no promises. That's not a horrible monstrosity, huh? That ain't bad. Got a radius of about 3. I'll draw a little line to demonstrate that. So the radius is this. That ain't bad. So really all we had to do was read the center and radius straight off of the circle. And it's not so bad. It's not so bad. Okay, so we feel comfortable. We feel like we can maybe graph these things. Let's find the equation of the circle with a center of 3, 6, and let's make it interesting actually. Let's make it negative 3 comma 0. Let's go off my notes and experiment around. How does that sound? Negative 3 comma 0 and a radius of 5. And all we need to do is find the equation of such a circle. All right, well, let's think about writing it in our standard form. Let's see, how's about, well, we know it's got to be x, it's going to be plus or minus something. Since the x coordinate is negative 3, we're actually going to put the opposite sign in here. And so it's going to be x plus 3 squared. And that's like the x portion of it. Plus, now we got to do the y portion. And here's where things get cool. Because you say, oh, the y coordinate's 0. So I can put y minus 0 squared. And now I'll do my best Jerry Seinfeld impersonation. But wait, no, never mind. I'm not going to do that. You guys, I don't know if you know who Jerry Seinfeld is. But wait a minute. What is y minus 0? What is anything minus 0, class? What is it? Might conjure up a couple words, but it's just itself. It's just itself. So to say y minus 0 is kind of unnecessary. You're just like, okay, it's just that. And so what you could do is you can bring this over here and just say it's that. And you're totally right. So if you don't see, if it's written in this form, but you don't see anything attached with the y like that, then you got nothing to worry about. The y coordinate is going to be 0. In fact, we can even go the extra distance and just delete the parentheses. And we can say it's this. And you're completely right. And now what we got to do is we got to say that's equal to the radius squared. So if the radius is 5, it's not just 5 on the right-hand side, it's 5, which is then squared. And then class, what is 5 squared? What do you guys got? 5 times 25, yeah. So 5 squared. So we can actually put the radius squared. We can put what it literally comes out to, which is 25. So this would be the equation of a circle with that center and a radius of 5. And we've just fulfilled exactly what the problem has asked us to do. Isn't that fun, guys? Raise your hand if you're having fun. All right, let's see. I'm counting. 1, 2, 3, 4, 5, 6, 7. I see 21 students with their hands raised right now. And of course, that's probably not actually the case, but we're going to assume it is. We're going to say it is, all right? A few things to note. We're about to actually so we just did this. This seems pretty straightforward so far, right, guys? You're like, okay, we can set up what the equation of the circle looks like. A few notes. Most of the time when you see an equation you graph, you have y all by itself on the left-hand side, if it's written the way we like. You have y all by itself on the left-hand side. You get all the business with x on the right-hand side. And then sometimes you might even call that f of x equals. You might get fancy with it. We can't do that with an equation of a circle in the standard form. In fact, we may not even be able to do it in general without losing information. So the way we think about how equations and graphing work, we kind of need to expand our minds a little bit. Another thing to note is that what if we wanted to square this out? What if we wanted to find x plus 3 squared? Just for kicks. What if we wanted to write the equation in a different way? Well, you can. You'll end up with this. You'll end up with that business. And so you can see pretty quickly it gets tenuous. Notice if it's written like this, if it's written in this form, and maybe you move the 9 over, suddenly you can't just read the center off the graph. And then if we did move the 9 over to the other side, we subtracted 9 from both sides. 25 minus 9 would be 16. If you did it like this, you can't read the radius either, because you'll notice that it's not written in the proper standard form. So wait a minute, this creates a conundrum. This creates a problem. Now you're tempted to say the radius is 4 because 16 looks like a perfect square, but that was actually just a weird coincidence. What if that was 18? What if that was 18? You can see that this equation here, it's still the equation of a circle. Now the radius is no longer going to be pretty like it was. This is still the equation of a circle though. So you're going to have to realize that while this is the standard form and it's the best form because you can read the center and radius right off of it, this is going to be sometimes what you see in the wild. And you'll have to realize that you're still dealing with the equation of a circle. If there was no y squared component, suddenly it's not a circle anymore. So the fact that there's both an x squared and a y squared component, and then the rest of the equation behaves in a certain way, that's actually rather telling. That's rather telling. So I can identify that this is the equation of a circle right off the bat. So in reality, what you're going to have is what we call the more general form of a circle, of the equation of a circle. And it's a lot less forgiving. It's going to have an x squared and a y squared component. And they have to, at least initially, they have to have a 1 coefficient. In other words, the coefficient here is 1. The coefficient here is also 1. They kind of have to, or they definitely have to. But then there could be some fancy business with x plus d generation x dx plus e y plus f This is the more general form of an equation where D, E, and F are real numbers. This might be a form of the equation you might see in the actual wild. And it's obviously a lot less fun. If you see a circle written in this form, you can't immediately read the center and radius off of it. So wait a minute, suddenly that becomes a lot more annoying. That becomes a lot more annoying. For instance, the equation we had just a few minutes ago, remember this one? This is written in the best form. There's not really a name for it, maybe the standard form versus the general form. But we could write this into that general form. We can do it by actually squaring this, foiling it out. Squaring this one as well, foiling it out. Let's see, you foil this bad boy, you're gonna get x squared minus x again, so it becomes minus 2x plus 1. Foil the second bad boy out, you're going to get plus 6y twice over, which becomes 12y, plus 36 equals 25. So you can see you can manipulate the way we want to write it, and you could write it in standard form. Why would you? Well, there's good reasons for doing it. For now, it's to demonstrate that you can do it, that the general form, the thing we don't like, exists. And so overall, you can move the 1 over, you can move the 36 over, and you'll get x squared plus y squared with a little manipulation. And you'll get negative 12 on the right-hand side. So all I did was rearrange the terms, move the 1 over, move the 36 over. And yeah, this one down here, this is the answer. This is gonna be the general form. And it's a lot less fun. How many of you guys would agree that's a lot less fun? That kind of takes the spirit out of it. And I would agree with you. Real quick, I gotta step out of the room for just a hot second. I'll be right back in just a couple minutes. Okay, so back to the grindstone. What we can do is we can start with something that's written in the form we like, and we could put it in a form we don't like. But what you're really gonna need to know how to do is to go from the form we don't really like, all the way back to the form we do like, in case you do need to figure out the center and radius of a circle. So let's try that out. It's going to involve completing the square. So let's see. What do I have for you, Space Cadets? I've got this equation, x squared plus y squared minus 6x plus 4y equals the negative 9. And what we're going to do is we're going to find the center and radius of such a thing. We can tell it's a circle. It's the equation of a circle. The thing that really gives it away is that there's an x squared and y squared in there, and then there's nothing else that's funky. It's just maybe there's an x term, a y term, and a constant. There's no square roots of x, x to the negative 4 power, none of that business. Okay, well, how are we going to do this? We're going to complete the square. We're going to reuse that completing the square protocol. We're actually going to do it twice. We're going to do it for the x's, all of whom live in Texas, and for the y's as well, separately. So let's see. The first thing I want to do is I want to rearrange the terms so that basically all the things with x are next to each other. And you can do this, right? Commutative property. I can move the terms around, rearrange them at my behest. I can move it so that the y terms together. Just a simple reordering. Now let's hone in and let's focus on the x terms. Now remember, if you were to complete the square, let's think. You're going to take half of this number here. You're going to take half of -6, which is -3, and you're going to square it. So first of all, half of -6 is -3, but then you square it, and you'll get 9. All right. Well, we've got 9. Now I'm going to append it. I'm going to add it on to here. So I'm going to end up with x squared minus 6x plus 9. Now, wait just a minute there, Sheriff. I can't just add 9 to only the left side of the equation, which is essentially what I'm doing. I got to add it also to the right side of the equation. So if I'm going to be adding 9 to the left side, I also need to add it to the right side, which by lovely coincidence, these are going to become just 0 in a moment. But let's wait a second to actually do that, because I also need to complete the square for the y portion. I also need to do that. So I look at this number, it's 4 in front of the y. I take half of 4, which is 2. Then I square that, and I get back to 4. And so what I need to do now, I need to add 4 to this left-hand side. I'm going to do it directly with the y's. So that's going to be plus y squared plus 4y. I'm going to add a 4 in there, but again, I can't just do it to one side only. So I need to add a 4 here as well. So all in all, or all in ALDA, you're going to get on the right-hand side, -9 plus 9 is 0, but add a 4 back onto it, and you'll get a 4 in total. Now let's pause for a minute. Now all of you are thinking, wait just a darn minute there, Josh. We started off with this thing in green here, and you just made it even nastier. You just made it even longer. Why would you do that? What are you doing, man? Well, the beautiful thing, remember when we complete the square, what that does is that makes each portion of this, it makes it a perfect square binomial, we call it. So, or a trinomial, whatever you want to call it. So this can actually become just x minus 3 squared. Straight up. Remember that? Remember that completing the square method? That's what we did. This all right here condensed down to this. Don't believe me? Well, try squaring this back out. X minus 3 times x minus 3, you get x squared. You'd get minus 3x 2 times, which condenses to minus 6x. Then you'd get plus 9. So yeah, it works out. How did I know it was just x minus 3 squared? Because the minus 3 was the half of this term. And now this next guy is also a perfect square trinomial. It's going to be y plus 2 squared, half of the term in front of y squared. And then the 4 is just a 4 on the right-hand side. Whoa, everyone say, whoa. You all have my permission to say that. You don't have to if you don't want to.
They did.
They did say it. Oh, the joy that brings to my heart. Thank you guys so much. Yes, we all say whoa because now this is written in that wonderful form we like. We used a little completing the square to manipulate things. And so now we can answer the question. This thing has a center and radius. The center, we can read it straight out of this business, and it's the opposite. So if it's -3 here, then the center is really going to have an x-coordinate of +3. And over here, if it's if it's plus 2, then the actual y-coordinate is going to be -2, the opposite side. And then the radius isn't 4, it's the square root. Oh, that's a terrible square root. It's the square root of 4, which is 2. So there you go. So the radii have been coming out pretty cleanly so far, because they just happen to be numbers that can, or, just integers, whole numbers. That's not always going to be the case. If for some reason, and it wasn't here, but let's mess up this a little bit. If for some reason this was like, I don't know, 71. Well, 71 is not a perfect square, which means its square root is going to look ugly. But oops. The radius then would just be the square root of 71, and that's just what it is, whatever that number comes out to. So the radius isn't always going to look pretty. That does make graphing it, something that you can't quite do by eye usually, using your eyes.
Yes.
But
No, that's exactly right. What? It's exactly right.
Yeah, I said 6, I meant 8.
what's that?
I was just trying to guess it to the nearest 10.
Oh, very nice.
I was just being a weirdo. Don't worry about it.
Is it like it's between 64 and 81, so it's between 8 and 9, right?
I picked 8.4.
8.4-ish, yeah. Somewhere in that ballpark. Of course, square roots of numbers that are ugly are as tenuous, it produces an irrational number, so it's ugly. But yeah, that's pretty cool. I do not have that ability. I'm not amazing with arithmetic. You're probably saying, well, Josh, teach math. And I say, well, you don't have to be great at arithmetic to teach math, believe it or not. Okay. So we talked about making the graphs of circles. We talked about how to actually glean information from the circle concerning the center and radius. Now, let's mess it up a little bit. Let's play around. Let's play around. Imagine, not dragons, but imagine you had a circle with this equation. Imagine you had a circle with this equation. So we're doing a little bit of a deconstruction of circles, just like Star Wars The Last Jedi was an unnecessary deconstruction of the Star Wars franchise. Look at this. What's wrong with this? Can anyone see what's kind of weird about this? Yeah, that -5 is going to create some problems. It's going to give us fits because it's written in the form we like even. We don't need to complete the square or do any of that business. Earlier, there was a negative number on the right-hand side, but after completing the square, that problem got remedied. But here, we're going to face that problem straight on. So this would theoretically, and I say theoretically because it's not going to actually be a circle. Theoretically, this would have a center of 6, -2. But its radius, theoretically, would need to be the square root of -5. Wait a minute. You're trying to take the square root of a negative, you got to bring I into the mix. And so that's actually not proper because we can bring I into the mix when we're talking about things in theory on paper. But how do you have a radius of square root of 5i? Because we didn't really talk about the physical interpretation of I so much. This is an imaginary number. So really, if you were trying to graph this radius makes no sense. So here's the low down skinny of it. This is not the equation of a circle in the real numbers, which is all we're going to concern ourselves with. So if you see something like this, it's a little bit nasty. But don't always assume if there's a negative number on the right-hand side that you're going to have that issue. That's only if it's written in the standard, in the nice form, the form we want it written. So this is not, it's not anything. Now, it is something if you go into another level of math called complex analysis, which we're not going to go into. But for our purposes, this is nothing. This is bupkis. Okay, so we're still playing around. We're still playing around. We're playing with our imaginations. Imagine the equation x plus 2 squared plus y minus 19 squared equals 0. Well, that's just a barrel of fun, isn't it, class? The center of this circle would be, take the opposite signs, would be -2 comma positive 19, not 10. What would the radius of this circle be? Well, you got 0 over here, so remember you got to take the square root of that number. Of course, the square root of 0 it's not anything mysterious. It is itself 0. Something fishy is going on. Something's rotten in the state of Denmark here. What does a circle with a radius of 0 look like? What do you guys think? Exactly. It's just a dot, right? We could say it's a singularity. It's an infinitely small circle that just exists at a very, very small point. Put another way, it's just a coordinate. It's just a coordinate on the xy plane. So this equation, even though it looks gaudy and it looks very large and it looks larger than life, it looks like a circle, this equation is really just the equation of a coordinate, of a point. And what do you suppose that point is? The center, yeah. So this one is kind of silly. In other words, if you were bored one day and you're sitting at home and you're saying, gosh, we can make all kinds of equations. We can make equations of lines. We can make equations of parabolas using quadratics. I wonder what the equation of just a single point is, of just a coordinate. This is it. You just make it like a circle with a radius of 0. And so it's kind of silly, but it is exactly what it is. So I just gave you guys a wonderful tool. I hope you are all very appreciative of that. So you now know how to make the equation of a coordinate. And it's almost silly, like, oh, it's just a circle with no radius. That's silly. It's almost not even a circle technically, but whatever. All right, finally, let's look at another one. We're still just kind of experimenting. We're playing around with this. We're just having a little bit of fun. Let's look at the XY coordinate plane. Let me move that a little bit. Let's play around with some ideas. We're going to hone in on the first quadrant here, the XY. So these quadrants are still here, but we're not really looking at them. Let's look at it. Now, I can't promise you this circle will be to scale. I will try for it, but I can't make any promises. But let's see if I can. Something like this. So we have a circle in the XY coordinate plane, and let's say that there was a point on it. Let's see, let's use a green dot. Let's say we had a point on the circle, and let's say that this was the point 3, 6, not 3, 6 Mafia, 3, 6. And now let's say on that same circle, but on facing 180 degrees away from it. 180 degrees on the other side. So it's not just barely over here. No, it's completely a full half rotation around the circle. Let's say we now have the point. There's another point up there. Let's say it's 9, 8. Okay, that's a lot of fun. I've given you 2 points on the circle. You have to know they're 180 degrees from each other for this next method to work. And then I say, find the center and radius of the circle. Well, wait a minute. What is it? What is it? What is it? How many of you hear crickets out there? How many of you are unsure of what to do? Raise your hand. Raise your hand. Find the radius in the center. I mean, I can draw the center, right? It would just be right here in the middle with Malcolm. But do I truly know how to find the coordinate of that? That's a different story. So let's talk about this. First of all, because they're 180, it goes a half rotation around the circle to get this other point. That means this line here, the line in the middle, is a diameter. So a few facts. The line in the middle is a diameter. It cuts the circle in half. It goes directly down the middle of the circle. And thus, if it's a diameter, it crosses through the center of the circle. So then the center of the circle is the midpoint between the two coordinates we have on the outer rim of the circle, 3, 6, and 9, 8. We're just spitting out some good old-fashioned American truth here. Okay, so let's start with that. We need to find the midpoint of these 2 points, and that's going to get us the center of the circle. Promise. So, to find the midpoint of 2 points, let's call them, I'll give you the formula, but I'll tell you why it makes sense. I don't like just giving a formula. Let's say that you have 2 points, x1, y1, and x2, y2, and we're only calling them those so that we can differentiate. This is the x coordinate of the first point, this is the y coordinate of the first point, etc. To find the midpoint, well, it's going to be this fancy formula here. Let's see if I can't write this out nicely. Nope. This is going to be the midpoint. But pump the brakes for a second. This looks nasty. It looks worse than it really is. You got subscripts going on. All we're really doing here is this. We are taking the average of the x coordinates. We're taking the average. Because the average of 2 numbers is the value that's perfectly sandwiched halfway in between them. So all we're doing is, okay, here's the 3 on the x plane, here's 9, and we're taking the average, we're going halfway in between them. That's all this is saying. Take the average of 2 numbers, add them up, and divide by 2. We're also just taking the average of the y coordinates. We're taking the average of the y coordinates. So we can actually do that here with great aplomb. Average of the x coordinates. Well, we got a 3 for the first x coordinate. We got a 9 for the second x coordinate. We average them, we add them up, divide by 2. You get 12 on top, divide by 2 equals 6. So the center of this thing, it's going to have an x coordinate of 6. So actually, I'll just put that right here. And now, to find the y coordinate, to find the midpoint, the y coordinate midpoint, we take the average of 6 and 8, which you might figure out is just 7. Just halfway between 6 and 8 would be the number 7. Don't believe me? Do 6 plus 8 and divide by 2. 6 plus 8 is 14, divided by 2. So the center as a whole is the coordinate 6, 7. So you can, I guess you can memorize this midpoint formula. You probably should have seen the midpoint formula, I think maybe in like Algebra 1 prior to this. You could memorize that, but I hate memorizing formulas. I like to know why we do things. And so just remember, this is just the average x coordinate, average y coordinate slapped together into a single point. All right, so that gets us half of our problem. That gets us half of what we need. But the other thing we need is we need to know the radius of this circle. Okay, so let's think. Let's think in geometric terms. We have these 2 points, 3, 6, and 9, 8. We know that if we draw the line between them, it creates a perfect diameter of this circle. Well, the radius is just half the diameter. The diameter is the entire line, but the radius is just from the center to any point on the circle. So let's do some more facts we know. I'll have to erase this. Sorry, midpoint fans. We already know the center. So a few more facts. Distance between the points 3, 6 and 9, 8 would be the diameter of the circle. Hopefully these terms like diameter, radius are not new to you. The radius of a circle is half its diameter. In other words, if we can just find the distance between the points 3, 6, and 9, 8, we'll know what the diameter of the circle is, cut it in half, and you now know the radius as well. It's that simple. So we might remember, how many of you guys remember the distance formula? The distance formula between 2 points, maybe you do, maybe you don't. I'll write it out here for you. Distance between 2 points, we'll call the first one x1, y1, and the second one x2, y2, and that's just a useful notation. You know, we could call it A comma B and C comma D, but this is a little bit better. I like it this way. The distance is a big old fat square root. And what you do is you take the difference in the x coordinates, and you square it, plus the difference in the y coordinates, and you square it, add them up, and then you take the square root of all of that. How many of you have seen that distance formula before? Everyone say, yeah, if you have.
Yeah.
Yeah, we've seen it. We got a couple minutes, and how many of you want to see why that distance formula makes sense? Anybody? How many of you really want to and aren't just going to placate me and say, sure, Mr. Gunther, yeah. How many of you really want to see it? Anyone?
They all said yes.
Oh, that's awesome. I love that. You guys are my friends. I get to go off on a nerdy little tangent here. It's not nerdy to be mathematically oriented. I probably shouldn't say that because it's my job. But yeah, no, let's look at why this distance formula makes sense. Because again, you might have seen it before. It turns out all it is an application of the Pythagoras theorem, of Pythagorean's theorem. If you really want to learn some cool math history and not like boring math history, I'm talking about there was an ancient Greek mathematician and philosopher named Pythagoras. And it turns out what Pythagoras was, he was actually just some really rich guy, and he had kind of a stable of mathematicians who were working under him. And anything that they found, any new mathematical discoveries they made, he straight up stole it from them and put his own name on it, slapped his own name on it. In fact, the way his organization operated looked an awful lot like a cult. So it's literally sometimes called the cult of Pythagoras. And if you know anything about cults, they get weird. So if you ever wanted to do a little cool history lesson, you can go talk about the cult of Pythagoras. But I digress. If you remember a right triangle, and what defines it as a right triangle is that there's a 90-degree angle somewhere in the triangle. And according to reasoning, there can only be one 90-degree angle triangle, if there is a 90-degree angle anywhere. And so you might call this, you might remember this is sometimes called the side A, B, it doesn't matter. Those are the legs of the right triangle. And then we reserve lowercase c for the hypotenuse, the longest side that's facing the right angle.
No, this is just you.
How many of you remember the famous Pythagorean's theorem? Anybody?
A squared plus b squared equals c squared.
You guys are on par today. Very good. That is correct. It says that a squared, which really a is the length of this side. It says that the length of one leg plus the length of the other leg, each of them squared, is equal to the square of the hypotenuse. Now, if we could, we won't, let's not do it, but we could actually prove that Pythagorean's theorem if we were bored, but let's not. For now, let's take Pythagorean's theorem on faith. Let's take it on faith for today. So you remember Pythagorean's theorem. So now let's apply that to an XY coordinate plane. And again, we can actually do it. It doesn't matter what quadrant each of the points is in, but I think it's convenient just for demonstrating purposes to focus on the first quadrant, the upper right quadrant, because all the numbers are positive. All the X and Y values are positive, and that just makes things a little simpler when we're demonstrating. Well, let's say you have 2 points. Let's say you have this point, and it's going to look an awful lot like the points we just had on our circle a second ago. And let's say you have this point. Furthermore, let's actually, should I do it? Yeah, let's go ahead and put values to those points. I don't know. What value should we put? How about we call this first point 3,6? Oh, and maybe we'll call this second point 9,8. Hey, that should look awful familiar to you there, Pilgrim. Well, if we wanted to find this distance here, it's a line that's at some kind of slope. So it's not just a matter of simple subtraction. You can't just subtract this point from that point. That doesn't make sense. Because normally in one dimension, you find the distance between two values just through subtraction. In fact, that's almost the definition of subtraction. Here, though, it's in 2 dimensions, so that won't quite work. But here's what will work. All we're going to do is we're going to say, let's use a different color. We're going to say that we're going to complete a right triangle here between them. All right. We don't even technically need to know what this point is. And then let me move this up so I have a little space here. We're going to complete this right triangle between them. And so what we're looking for is this distance here. Remember earlier on the right triangle, we called that C. Now down here, we would need to know this distance. We'll call it A maybe. But think about it. A is strictly a horizontal line. So A is just going to be the difference between the X coordinates of these points because it's entirely, parallel to the X axis. So I would take 9 minus 3 to find the length of A. Ooh. And now remember, this graph's not to scale because 6 and 8 looks like a much bigger jump than it is. It's not to scale. But now B is a vertical line, so it only cares about the Y coordinates. B is just going to be the difference between the Y coordinates, 8 minus 6. That's going to be that vertical distance there. Ooh, okay. So this is all starting to kind of click a little bit. Now, the reason I haven't actually done 9 minus 3, you'll see why in a second. But we know 9 minus 3 is just going to be 6. We know 8 minus 6 is just going to be 2. But if we applied Pythagorean's theorem, which says that A squared plus a B squared equals a C squared, we could then substitute the values we have for A and B. We could say that A is, well, it's 9 minus 3, but then we got to square it because Pythagorean's theorem says to square that. Let me give myself a little more space here. A there squared, you get back over there, Pilgrim. Yeah, that's A squared, just 9 minus 3 squared. And maybe you're starting to see it all kind of fall in place. Plus b squared. And then that is going to end up equaling that unknown side squared. And now remember, our whole point of doing this is to find c. It's to find the length of this side here, because the length of that side is the distance between the 2 points. Since c is being squared, we already learned the square root property that says we got to take the square root of both sides. So we're going to take the square root of both sides, and suddenly, yeah, whatever. Nope, we can't. I need to give myself a little more room. Technical issues. And now suddenly when we take the square root of both sides, ooh, that looks an awful lot like that distance formula, doesn't it? Yeah, I think it does. And so suddenly we do all this and it just looks like the distance formula. It's just the difference in the x values squared plus the difference in the y values squared. Then you take the square root of that entire thing there. So that's pretty awesome, I think. That's really kind of cool. That's why the distance formula makes sense. And so now you'll recall, and now I'm going to have to hit undo a lot to get back to what we had a minute ago. But now you'll see if we finish off this calculation here, 9 minus 3 is 6, so you're going to get 6 squared plus 8 minus 6 is 2. You're going to get 2 squared. Keep it going, keep it going. Now 6 squared is 36 plus 2 squared. It's going to become 36 plus 4. And it's going to end up being the square root of 40. So simple calculation, square root of 40. Now let's... No, you know what? That's just going to be awful. Let's just rewrite. So now we go all the way back to our circle. We go all the way back to our circle that we had. Looked something like this, give or take. We remember that it had a center. The center of that circle was the point 6, 7. It had coordinates 9, 8. And down here was 3, 6. So it's the center of 6, 7. And now it's going to have a diameter of the square root of 40. Well, you remember we wanted the radius. So the radius is just going to be the diameter cut in half. How about that? How many of you would say that's pretty cool, huh? Anybody? Cool? Yeah, it's okay. It ain't bad. It ain't bad. What if we wanted to make the equation for this circle? Let's make the equation. Okay. Well, we remember the standard form. It's going to be x, and then it's going to be minus 6 because 6 is the x coordinate of the center, plus, now we got to do y minus 7 and square it. And then here's another interesting thing. This almost itself looks like the difference quotient. I'm sorry, not the difference quotient. The distance formula. And it looks like all kinds of Pythagoras theorem things are floating around here. And that's exactly right. That is 100% what's going on here. But we won't quite go into that level of detail. And then it's equal to the radius squared. So we're going to take this and square it to complete the equation. And then just one last quick note. This is ugly. This is not very pretty to look upon with our eyes. So let's just simplify it real quick over here on the side. If we square that, we got to square the top and the bottom. We got to apply it to both top and bottom. And that's actually an exponent law. So I can square the top and the bottom. Of course, the square root of 40 squared, the square root and the squared cancel each other out. You just get 40. On bottom, 2 squared is 4. And then 40 divided by 4 is 10. So actually, this thing just becomes equals 10. And now this looks just the way we'd want it. That looks just like the equation of a circle. The radius is square root of 40 over 2, which apparently can also be written as square root of 10 because we would take the square root of this number. How about that? Does that make sense, my friends out there in the Zoomosphere? Yeah, lots of stuff. So that's going to be it for section 2.2. We are going to start the next section here. We got a couple minutes left. But one thing I'll note, of course, I'll be uploading video of this to the YouTube channel. Go subscribe to my YouTube channel, which is, I hate saying that. Subscribe for your educational value. I'm not going to post Fortnite videos or whatever, stupid Minecraft things or stuff. I'm not trying to monetize the channel. It's literally just an educational channel. And then later on, I'll monetize it, right? No. So anyways, go subscribe to the YouTube channel. You can see videos of all of our past lectures. Like I mentioned at the beginning of class, if you go into Canvas, if you go into the modules in Canvas, I have posted new videos for section 2.2, and I will post some for section 2.3. These are videos that I have found that I think would be beneficial to you. And so, yeah. So we talked about circles. Now, let's talk about functions. This is the next section, functions. Now, the section 2 is a little bit funky because section 2 ultimately is interested in graphing. It's interested in visualizing certain mathematical relationships or equations, functions, things like that. The problem is, in order to properly visualize something as on the XY coordinate plane, you got to go into some pretty weird definitions. So we're actually, in this section, we're going to define just something simple called a relation. And then we'll see that some relations are also functions. And a function is something you want to be. That's where I want to be, living in Beverly Hills. So we're going to do a few quick definitions. And again, this is going to get a little abstract at first. It's not bad, but it is a little abstract. It's not something you can just put your hands on. A relation is a set of ordered pairs. Oh, that's dumb. A relation is a set of ordered pairs. I don't like that definition, but I'll underline it. I'll underline the word relation. That's our new definition. That's kind of silly. It just, what do you mean, like a set of ordered pairs? Like, how about, assume that's a set bracket. That's not a good one, but I can't draw. Okay, here's some ordered pairs. -3, 6, okay. 4, 5, okay. 4, 7, okay. That's some ordered pairs, and I've gathered them into a set. So wait a minute, Josh, you're telling me that is a relation? Yeah, that's exactly what it is. That seems silly. Why would we create a special definition for that? That's dumb. It's just, oh, just put some ordered pairs together and you can make them up, right? Well, not exactly. What an ordered pair really is at the end of the day, it's something you can go graph on the XY coordinate plane. Sure, you can put a dot at the proper place. But more importantly, what it does is it defines a procedure where if you were to plug in one value, put one value in there, you get another value spat out. Or at least that's how we're going to interpret it at this moment. So imagine I have some kind of procedure, some kind of machine that takes in a -3, does some magic business to it, and spits a 6 out of there. Now, you may have heard terms like independent variable, dependent variable. And yes, that's kind of the thought that goes on. X is the independent variable. It kind of has leeway over what its value is going to be. The Y variable, the Y coordinate, is going to be dependent on the X coordinate. So we are getting really abstract. Imagine you had an XY coordinate plane, and let's say you just had a line, a linear function in the XY axis that looked like that. That defines a bunch of coordinates. That's everything that's on the line, every point on it. So for instance, down here, if you could plug in a -1 for X, you might get a -2 for Y. The line is simply a machine that assigns values of Y based on X values you pick along the way. That's all it is. This is even more abstract. Only now, down here with a line, you might have had an equation for that, like Y equals 3X minus 4 or something. And now you have an explicit way of figuring out what the Y value is based on an X value. That's what this does. But up here, you don't have an equation. This is literally telling you what those assignments are directly without you needing to plug things into an equation. This is saying whatever X value, okay, if you pick -3 for X, boom, this is the Y value that must partner with it. If you pick a 4 for X, this is the Y value that must partner with it. Well, wait a minute, so is this. So is this. So this is still a relation. It's, again, this is awfully abstract. It's a little bit weird almost. But that's kind of what's going on here. But now let's define the big bad boy, a function. A function is a relation, so it's either a set of ordered pairs or it's some kind of definition that gives you the idea or the relationship between X and Y. A function is a relation where for each distinct value of the first component just of X is usually what we use, X and Y, where for each distinct value of the first component, there is exactly one, no more, no less, there's exactly one value for the second component. This is incredibly vague. This definition is extremely vague. They don't even call it X and Y because you can generalize it and use any variables you want. So this is a very vague definition. All it says is that a function is some kind of relation. So it's some kind of set of ordered pairs or perhaps an equation that relates X with Y, except anytime you pick an X value, a distinct X value, only one Y value can come out of it. So in this relation, if you pick -3 for your X value, for your first component, the Y value, the second component that is attached with it, is going to be 6. But you run into an issue because if you pick 4 for your X component, for your first component, this thing is saying both 5 and also 7 are the Y values attached to it. So this is still a relation. This is still a relation, but it's not a very good one. A function says, nah, you can't have any of that business going on. A function is the law, and the law is coming to say, no, sir, not today. The function says that you can't have this funny business going on, that if you have an X value, it can only go to one Y value, exactly one Y value. Here, this number 4 is trying to go to 2 Y values. So we're out of time. We will deal with a function next time. We'll look at some examples of things that are functions and things that are not, that are merely relations. You guys have a great day. Remember, if you can make it to the 3 p.m. review session, it'll be on the main campus of Weatherford College in the academic building, room 129. Wear a mask. Y'all have a great day.